interfaces in the last class. And so we looked at the iterator interface very quickly. Right? So remember, an iterator is an object that knows how to iterate over a collection or iterate over a sequence of values. Right? The two critical methods are has next and next. Right? Has next returns true if there's something left to iterate over. Next gives you the current element in the iteration and then moves to the next element. Okay, there's a related interface called iterable. Right? The iterable interface says that your object can be the target of a for each loop. Right? So if your class implements iterable, then you can write a for each loop over the objects of your class. Right? So list implements iterable, and set implements iterable. Right? And that's why you can write a for each loop on a list or a set or a map. Iterable says that your object must provide an iterator, and then it uses the iterator for the for each loop. Right? So there's only one method in iterable. Now the reason this is an interface is because by making an interface, a class that implements the interface is advertising the fact that you can write a for each loop on it, right? That it has an iterator method. So anything that gets one of your objects, any method that accepts an iterable object can take one of your objects and they can just iterate over these elements in your object. And so we're going to implement a class that provides both iterable and iterator. Right? And what we're going to do is we're going to emulate a Python for each loop. Right? So in Python, you've got a loop. It loops over the elements in this object called range. Range is just a sequence of values between 0 and, in this case, 10, not including the 10. Right? So range is just an integer sequence of values. To do the same thing in Java, you need to make your own class, right? And you need to make an object of type range. So it looks almost exactly the same, other than the new. All right, so let's make this class. So we started making this class called range. It implements iterable, right? A range has a start and a stop value. It provides the iterator method because it implements the iterable interface, right? And the iterator that it provides is one of these range iterator objects. Right? Now remember, range iterator is defined inside of the range class itself. Right? And so range iterator is a private inner class belonging to range. Right? The fact that it's a private inner class means that only range objects can make a range iterator object. And so in Java, so this is specific to the Java language. Other languages don't use these terms specifically. So a nested class in Java is a class that's defined inside of another class. Normally when you do this, the only purpose of the inner class is to serve the other class. Right? So if your nested class would actually be useful on its own, then you would normally make it as a separate class. If your class implements iterator, then it almost always, the iterator is implemented inside the class. Right? Because it doesn't make sense to have an iterator without an object to iterate over. Right? So it doesn't make sense to have a list iterator if you don't have a list. In our case, it doesn't make sense to have a range iterator without a range. Right? Okay, so this class is actually an inner class. Right? So the definition of an inner class is weird. So it's defined as by using the negative. Right? So if your class is not declared as static, then it's an inner class. Right? So this class here, not static, which makes it automatically an inner class. If you make it static, there is a subtle but important difference. Right? And I'll describe the difference in a later lecture. For now, it's an inner class. Objects of the inner class always have a reference to the outer class object. Right? So every range iterator has a reference to the range that it iterates over. Right? And that makes sense. Right? If you have an iterator over a range, it needs to know what range you're iterating over. If you have an iterator over a list, you need to know what list you're iterating over. Right? Now, an inner class object is allowed to access the fields of its enclosing class. Right? So every range iterator, right? So every one of these objects has access to the start and stop field of range, which again makes sense. Right? The iterator needs to know where is it starting from and where is it stopping at. Right? Okay, so what exactly does this object do? Well, it's an iterator, so it needs a has next and a next method. Right? When you make one of these objects, right, you want that object to start at the beginning of the range. So if you have a range from 0 to 10, the iterator should start at the number 0. Every time you call next, you return the current value that the iterator is at. Right? So when you make a new iterator, it starts at 0. If you call next, you get back 0. And then it advances the iterator to the next position. So the next time you call next, you'll get 1. The next time you get next, you get 2, and so on and so on and so forth. Right? Next is defined such that it throws an exception if there's no other values left to iterate over. Right? So if you get to the end of the range and then you call next again, the iterator should throw an exception. HasNext simply tells you, are there more elements to iterate over? Right? So if you're not at the end of the range, HasNext returns true. If you're at the end of the range, HasNext returns false. Right? So that's it. It's pretty easy to implement this thing. It's basically a counter. Right? So our range iterator, So our range iterator implements the iterator interface. Right? It's an iterator over integers because the iterator always returns an integer value every time you call next. So what does the constructor do? So the constructor makes an iterator and it sets the current value to the starting value of the range. Right? Now notice the way that you access the field in its enclosing object. Right? The syntax is very awkward. And I'm not sure why they did it this way, but that's the way that's how you have to do it. Right? So if you want access to the start field that belongs to range, you write range.this.start. And that gives you access to the start field. If you wanted access to stop, you would write range.this.stop. Right? There's no way to get around using this or range as far as I know. Right. Okay, what does HasNext do? Well, HasNext returns true as long as there's still values to iterate over. Right? It returns false if there aren't any values to iterate over. So in other words, as long as the current value is less than the stopping value, there's still some values to iterate over. Right? So HasNext is easy to implement. And then finally next returns the current value. Right? So the current value is just this dot value. Right? So we're going to return that. Right? But before we return it, we're going to also increment the value by 1 so that the iterator is at the next value the next time next is called. If there are no more elements, throw an exception. Right? And you just use HasNext to check that. And so in this particular case, the iterator is basically just a counter, right? Counts from 0 up to the stopping value, right? -1, I guess. And that's it, right? So it's pretty easy to implement. And now, if you really, really wanted to, you can write your counting style loops this way, right? Using the range object. You wouldn't normally do this in Java. The reason being, you have to make an object. And then the way that the code that's generated actually uses an iterator. So it's always calling HasNext or next, right? Whereas with a counting style loop, everything's just primitive values. And so it's much easier, it's much faster to manipulate the primitive values than it is to go through an object and call a method, right? So the regular counting style loop is much more efficient in Java, right? But if you're a renegade Python programmer, you can do this sort of thing. Okay, so there's an example. It's a rather complicated example, actually, of implementing an interface. Right? This one actually implements 2. The reason that I'm showing you this example is because later on we're going to be creating our own lists and our own maps maybe, and our own stacks and queues, and we're going to implement iterator for all of those classes. Right? And so the implementation of iterator is a little bit more complicated when you start to try to implement an iterator for those objects. Okay, suppose you want to make your own interface. So interfaces turn out to be enormously useful in Java and in most other object-oriented programming languages. They show up everywhere in the standard library, which kind of suggests that they are, in fact, very useful. It's easy to make your own interface, right? Mechanically, it's easy to make your own interface, right? Instead of class, you just use the word interface. And then everything's public, right? And so it's pretty straightforward, right? If I want to make an interface, I want to make an interface called printable, right? So I just say public interface printable, right? And now you just list the methods that you want every printable object to have. So printable is an interface for objects that can be printed to standard output, right? This is not a particularly useful example, right? But it's very simple. Okay, so what method do I want? Well, you just add your methods. They're all public, right? You don't put in the implementation, so everything just ends with a semicolon. Right? So printable has exactly one method, public void print. Right? If you call print on a printable object, it just prints the string representation of the object, the standard out. Right? And now, you can take one of our existing classes, modify it so that it implements the printable interface. Right? So for example, point 2, right? We can say that it implements, so it now currently implements comparable, right? But we can also implement the interface printable. Right? And so you just separate the interfaces with a comma. And you can implement as many interfaces as you like in a class. Right? I don't think there's a predefined limit to the number of interfaces you can implement. Right? And in fact, many of the Java standard library classes implement 5 or 6 interfaces. Right? So print is easy, right? So as soon as you say you implement printable, you have to provide a print method. Right? And print is just calling system.out.println and then calling toString on the object to print the object. Right? So very easy. So now you can just say, if you have a point 2 object, you can just write p.print and it prints it. Right? So that saves you a little bit of work. You don't have to write system.out.println anymore. Right? So that's why I said it's not the most useful interface in the world, but it illustrates how you would create one. Okay, so now we're going to start creating other interfaces. The motivation here is going to be data structures. So I think you guys all know what a stack is, right? You all are taught what a stack, so I don't have to go through this very quick. I'll just go through this really quickly. Stack just represents a stack of objects, right? What did they call the operations? Did they call them push and pop for you guys? Okay, so all stacks can push and pop. I guess you know what they do, right? I don't have to. I don't think I have to draw this picture for you. Okay, did they tell you where they're used? Or did they just tell you what a stack was? So it turns out they're used quite a lot. The most common one that you would have seen, although you probably didn't know it was a stack that was doing this, is when you have a program where you can undo and redo stuff, it's almost certainly implemented using a pair of stacks. Right? So the way it works is every time you do something in your program, some object gets created that represents what you just did. Right? So normally it's called command. Right, so some command object gets created that represents you just typed in some string in your word processor. Right? If you click undo, that command object gets pushed onto the undo stack, and whatever you did gets undone. Right? If you click redo, whatever's on the undo stack gets popped off that stack and goes pushed onto the redo stack. Right? So it's a pair of stacks that just operate, that go back and forth. But the way they work, so it's kind of cool the way that works. In old school computing science, you used to be taught how to parse text, right? So anything that reads a computer program, your compiler, for example, has to read your program. It used to be the case that you were taught how to do that sort of thing. It's a somewhat dry application of computing science. But it turns out to parse structured text, it's often useful to use a stack. Your program, so you're a Java program that's running on a Java virtual machine, or a C program that's running on some system that supports the C runtime, actually uses a stack to record which methods, or in C, which functions are currently running. Right, so there's actually is that me or somebody else? Okay, sorry. So there's actually a stack of function calls that kept track of. Right? Finally, if you have a recursive method and you want to turn it into a non-recursive one, one of the classic ways of doing it is to use a stack to keep track of the information that's being stored in the recursion. I guess you've sort of seen this before. So this is a dumb way to reverse a sequence. Right? So if you have a list that you want to reverse, you can use a stack to do so. That's me, right? Yeah. What's going on? I think I have a stuck key somewhere, is what's happening. Okay, Let's hope that goes away. Okay, so this is a dumb way to reverse a list. You shouldn't do it this way. Right? So to reverse a list, the way you should do it is you should swap the elements one at a time, right? So swap the first and the last, swap the second and the second last, and so on and so forth, right? The reason you should do it that way is because it's space efficient. You don't make a second data structure. If you wanted to, though, you can make a new stack. You can use a stack to do this, right? So you take the elements from your list T, and you just push them onto the stack, right? So for every element in your list that you want to reverse, push it onto a stack, right? Now, while the stack isn't empty, just pop the stack and push the result onto and add the result to your reversed list, right? And that will reverse the list. Uses twice the amount of memory than you need to, so it's not a great way to do this, but it works, right? And it works because the stack is last in, first out, right? Or first in, last out. Here's a picture if you really want to see it. There's your list, right? I'm just going to push all the elements onto a stack, so A, then B, then C. Right? I'm just going to pop all the elements out of the stack and put them into the result, and you reverse the list. Okay, so stack looks a lot like a list actually, right? If you push an element onto the top of the stack, sorry, this is really annoying. I don't know what's going on though. It might be Firefox. So I got mail, and I have. Well, let's just kill that and see what happens.
Do you need your volume though?
Hey, good point. I do not, in fact, need my volume one. Thank you. All right. So implementing a stack, it looks a lot like a list, right? So if you have if you push an element onto the top of the stack, that sort of looks like adding an element to the end of a list, right? So let's just go back here. Right, so whenever I push an element, onto the stack, right? If you imagine this is a list that's growing this way, then pushing an element onto the stack is like adding an element at the back of the list, right? When I pop elements off the stack, it's like removing elements from the end of the list, right? And so that kind of suggests that, hey, if I want to implement a stack, I can just use a list, right? So here's my stack, right? Internally, I have a list called stack. Probably should have called it something else, but oh well, right? So there's my array list. To make an empty stack, I just make an empty array list, right? To get the size of the stack, I just return the size of the list, right? To add an element to the stack, so this is a stack of strings, right? So to add an element to the stack, I just add an element to the end of the list. And to pop an element from the stack, I just remove the last element from the list, right? So you remove by index. So the index is always the size -1, right? For an array list, adding an element at the end of the list is usually in O1, but not always. Every once in a while, it's in ON. And we'll see why precisely later on in the course. To remove an element, though, that's always in O1. So this is actually pretty efficient implementation of a stack, right? And it's also very easy to do, right? You just use composition, right? So a stack is just a composition of a list, right? And away you go, right? It's still an aggregation of its elements, though, right? But it is a composition of a list, right? Why is it a composition? Because there's no method or constructor, right, that exposes our list, right? Here we return an element, but that's fine because it's not a composition of the elements, right? But nowhere do I return a reference to the actual list, so it's a composition. Now, there's other ways to implement the stack, right? And you've seen them already in your C course, right? So how did you implement a stack?
We had to do an array and a linked list.
You did both. Okay, so that's good. So you can use an array, or you can use a linked list. For your stack implementation, did it have an arbitrary size or fixed size?
We did both, I think.
Oh, good. Okay, so you've done a lot already. That's awesome. Okay, so you can use an array to store the elements, right? Or you can use a linked structure to store the elements, right? What are the advantages and disadvantages of the two?
The array, if you're using the same amount of storage, even if it's empty.
That's true. That's one of the disadvantages. Yeah. What about speed? It's actually, well, so in terms of computational complexity, it turns out the linked structure is actually faster. So it's O1 if you use a linked structure for both push and pop. If you push an element into a full array, you have to expand the size of the array, right? You guys did that? Yeah? So you have to expand the size of the array. That's ON. So every once in a while, you have to expand the size of the internal storage of the array. So that takes ON. With a linked structure, it's always O1 to link to the end, assuming you're keeping a reference to the last node. I don't know if you guys did that or not. Did you? Yeah? Okay, so that's good. All right, super. So, so in a language like Java, what you can do is you can create an interface for your stack. Right? So you create an interface called stack. You say that every stack has, right? Every stack has a size method, it has a push method, it has a pop method, right? And now you can create several different implementations of stack, right? You can use an array-based stack, you can use a list-based stack, you can have a linked structure for the stack, right? And then you can let the users pick which one they want to use, because your different implementations all have different trade-offs and advantages, right? And so you create an interface, implement the different versions, and let the users pick which is the most appropriate type for their purposes, right? And that's why in the standard library, there's a linked list and an array list. There's a tree set and a hash set. There's a hash map and a tree map, and a linked hash map, right? It's up to the user to decide which of the different implementations is most appropriate for the problem that they're solving, right? And so the interface gives you the flexibility to create different implementations of the same thing, right? And then the trade-offs and advantages of the different implementations, the user gets to pick which ones they want to deal with. Sorry, I just have to pull up, oh, now I need Firefox again. I just got to pull up the next lecture. Oh, oh. Well, I guess it means it's an early weekend because I don't actually have a copy of this lecture on this computer, I don't think. Let me just quickly check. I would need number 21, which I don't think I have. Oh, wait, that's not what I wanted. Is it here? I don't think I have it on here. Yeah, I just tried. It's not. It says available.
Just click connect.
Is it?
Yeah.
Why is it making me sign in? Sorry. Okay. $21 stacks, all right. Okay, sorry about that. I'm going to, well, let's do this. This is actually sort of useful. Okay. Did they show you how to convert a recursive method or a recursive function into a non-recursive one using a stack? They ever do that? Okay, so it's often the case, and this is going to be true if you take the algorithms course. It's often the case that to create a function, It's a lot easier to create a recursive function than it is to create a non-recursive one. This is especially true when you are working on trees and graphs. So the problem is, though, in practice, recursive functions can only solve problems up to a certain size, and then you run into a problem. And that's because of the way that recursion is implemented in most computing languages. Right? So here's a little function called power of 10. Right? So it computes, what does it compute? 10, oh, sorry, it computes 10 raised to some exponent n recursively. Right? Now, you would never do it this way. This is just for illustration purposes. Right? So how would you do this recursively? Well, our base case is if n is 0, right, the result is 1. This only works for positive values of n. Right? So if n is 0, the value is 1, the result is 1. Right? Otherwise, the result is just 10 times, right, the power 10 times 10 to the power n minus 1. Right? And how do you compute 10 to the power n minus 1? Well, you just use power of 10 again. Right? And so that recursively computes 10 raised to the power n. Right? So what happens when you run this thing in a programming language like Java or C, right, is the following. So I'm going to call 10 to the power 3. Right? So somewhere, the value of x, right, is evaluated as this function called power of 10, 3. Right? Now the way this works in languages like C and Java is when you run a function or a method, that thing has to run in memory somewhere. Right? So somewhere in memory, the method power of 10 pops up. Right? What actually pops up is the parameters that belong to the method. Right? So n, right, is the parameter. And any local variables that are in the method, they also appear in this chunk of memory. Right? So our method here just has one local variable called result. Right? And then some other stuff also gets pushed onto the stack. So some other stuff is also here, but it's not shown. Right? So that method there runs on what's called the call stack. Right? So what does this thing do? Well, it gets the value 3. Right? So is that a base case in the method? The answer is no. Right? So the line of code that says the result is equal to 10 times power of 10 to the power 2 runs. Right? So what does that do? Well, that calls a method. That method has to run somewhere. Right? Now, it's not the same method. Right? It's a new instance of the method that runs. Right? So it's not the same method. It's actually a new copy of the method that runs. Right? And it gets the value 2. Right? So is that a base case? The answer is no. Right? So that causes that line of code to run, which involves another method call. Right? So another method appears. Right? And that calls, that value of n is 1. That's not a base case. So that calls another method, right, which now appears. Right? So that gets the value 0. So now the result is known. Right? That method knows its result is 1. And it can return that 1 back to the method that called it. Right? So notice what this looks like. This looks like it's a stack in reverse. Right? It's growing down. As soon as it evaluates the return value and returns the value, right? So it returns the value back to the caller, this method disappears. Right? So in other words, it gets popped off the stack. Right? And now this method has the result 10. So it can return its value back to the caller, and that gets popped off the stack. Right? That can return 100 back to the caller, and it gets popped off the stack. And then that finally has a result which it can return back to the caller, and then it gets popped off the stack. Yeah?
Does this free the memory every time it?
Yes.
Okay.
Yeah. So it doesn't actually free the memory. So the way it works in C is that you have this chunk of memory called the call stack. And every time something gets popped off the stack, the C runtime system knows, it just adjusts an internal variable to say where is the next available free spot on the stack. Right. So look, if you have a recursive, so this is the problem with recursive methods, right? They typically end, if you try to solve 10 to the power of, say, 1,000, you end up with 1,000 copies of power of 10 on the call stack. Right? the call stack has a finite size on, well, it has a finite size in C and Java anyway, right? And so if you end up calling too many, or if your recursive problem tries to solve a problem that's too big, you run out of call stack space, and your program crashes. So there's a built-in limit to the size of the problem that you can solve using recursion, right? You eventually run out of call stack space. And so in practice, what you want to do is you want to take your recursive method and turn it into a non-recursive one, right? And the way you do this is you basically simulate what the Java virtual machine is doing when it's actually running a recursive method, right? So that sequence of pushing stuff onto the call stack and popping them back off, you just emulate all that using your own stack, right? So whatever information you need to solve your problem, you push that onto a stack, right? And then you pop it off as you need to make use of that information, right? So in power of 10, what needs to be done when each recursive call returns, right? So every time you return from a recursive call, right, you're going to multiply the return value of the recursive call by 10, right? So remember the line in the code is, right, 10 times the return value. Right? So each recursive call that is not a base case pushes a 10 onto the stack. So that's what we're going to emulate, right? We want to multiply by some power of 10. So we're just going to push 10 onto the stack each time, right? And that's so that we can remember we want to multiply the return value by 10 each time. Okay, what happens to the value of n every time you call the method, right? Well, it goes down by 1. So what does this look like? To convert that recursive method into a non-recursive one, you make a stack, right? So it's a stack of integer because this is an integer problem, right? Here are the recursive calls, right? So while n is greater than 0, you're just going to push a 10 onto the stack, right? Which simulates returning the 10 from the method each time, right? You're going to decrease n by 1 to simulate the fact that every time you call the recursive method, n goes down by 1, right? And so this runs until n is 0, right? In other words, until you've pushed n copies of 10 onto our stack, right? And now you just emulate the multiplication process. Whoops, sorry, right? A recursive call that reaches the base case results in a 1. So now we're going to accumulate the sum, right? So there's our base case, right? Our result is 1, right? And now I'm just going to unwind the stack, right? Every time I pop something off the stack, I'm going to multiply it into the result, right? So pop the stack until it's empty, multiplying the values as you go, right? So while the stack's not empty, take the result and multiply it by the popped value, right? And that gives you back, and that gives you the recursive version of that gives you the iterative version of the recursive method that we were just looking at. Now this seems needlessly complex, right? You could just write a little loop, multiply 10 by itself n times, right? But if you have a more complicated version of a recursive method, then basically this is basically what you end up doing, right? You emulate what the computer system would have done anyway when it made this sequence of recursive calls. It becomes a lot harder to do. You have to figure out exactly what information do you need to keep track of in the stack, and what do you do with that information when you pop the stack. So it's not so easy to do as this, but it's the same idea, right? So obviously that example is way too complicated for computing the powers of 10, but it illustrates the basic idea. All right, so if we want to implement the stack using, what are we doing here? If we want to use, so you know how to implement the stack using a plain array, right? So let's just quickly go through the implementation, and hopefully it's similar to what you guys did in your previous course, right? So in Java, if I want to make a stack of int, right, I'm going to have an array to hold the values, right? And you're going to keep track of where in the array is the top of the stack, right? I assume that's the way you guys did it in your previous course, yes? More or less? Yes? Okay, so you didn't grow the array every time, because that'd be dumb, I hope they didn't show you that way, right? Okay, so you're just going to keep track of where the top element is every time. Right? And so it's going to look exactly like it looks like in C. Right? So in our constructor, I'm going to make an empty stack. So I make an array that has some capacity. Right? So in this case, it can hold 16 elements. Right? For the top index, I'm just going to say it's at -1. So the -1 is an invalid index. So that indicates that the stack is empty. Right? And so that's the picture of what our empty stack looks like. Right? In Java, all the values are set to 0. Right? And the top index is -1. Right? To push a value onto the stack, well, you guys know what to do, right? You increment top index by 1, and then just set the array element to the pushed element. Right? So I'm going to push 7 onto the stack. Top index becomes 0. Put a 0 into the array. Right? Push a -5 on, top index becomes 1. Put a -5 into the array. And so, right, popping a value is easy as well. Right? You get the value at the top index, decrement the top index, return the value. Right? So if I have 7 and -5, right, when I pop the stack, I'm going to return the -5. Top index goes down to 0, right? And I don't care that the 5 is there in the array. Right? If you want to, you can overwrite it with 0, but you don't have to. Right? So pop, what does it look like? Right? So in Java, you're going to test a bunch of things, right? You're going to test, is the stack empty? Right? If the stack is empty, you're going to throw an exception. Right? If you're doing this in C, you may or may not test whether or not the stack is empty. Right? You want to get the returned value, so you just look in the array at the current top index. Right? You just adjust the top index down by 1, and then you return the element. Right? So what does the stack look like what does the stack look like before it's full? Just before it's full. Right? So your top index is 14 in this case. Right? So I can safely do one more push here. Right? So when can you push? So if the top index is less than the length of the array -1. Right? Not less than the length of the array, but less than the length of the array -1. Right? If it is, I can just increment the top index by 1 and set the element in the array to the pushed index, the pushed element. Right? Now, the else part is, what do you do if the array is full? Right? So if you run out of capacity in the current array, you need to add capacity. Right? So what do? You make a new array. Right? Now, when you make the new array, you have to decide how much bigger is the new array. Right? So we'll talk about that in a second. Once you have your new array, you're going to copy the old array into the new array. Right? You're then going to set this.arr to refer to the new array. And then you can go ahead and push the element onto the stack. Okay, so if the stack is full, right, make a new array. Right? Now here, I'm going to make a new array that's twice the length of the old array. Right? What did you guys do in your previous course? Do you remember?
I think
Basically the same? Okay. So this is actually important what you do here. When you increase the size of the array, it has to be, the new capacity has to be some multiple greater than the old capacity. Right? So in other words, you have to multiply it by something that's greater than 1. Right? If you add a fixed amount every time, so if you did plus, say, 100 or something like that, right, then it turns out the computational complexity becomes, it turns out that if you always add a constant amount, this no longer guarantees what's called average case O1 time. Right? So the technical term is amortized complexity. Right? If you just add a constant amount, it turns out that this degrades to O of n. Your worst case degrades to O of n. Sorry, your average case degrades to O of n. Right? If you multiply the capacity by some value that's greater than 1 every time, you can mathematically show that the average case is O1. Right? So it actually is important that you multiply by some value greater than 1 here. Right? Once you have your new array, copy the old array into the new array. You can just use a loop. Right? Set your current array to equal the new array, and then go ahead and push the element onto the stack. Right? Notice that's recursive. right? It's actually recursive, this implementation, right? It calls itself, it calls itself to push the element onto the stack, right? But as soon as it does, it falls into the base case, so it's fine. Okay, so in C, you would malloc that new array, right? Or you would realloc that array, right? Then you would copy it either with a loop or with memcopy, right? And then you would do something similar here and here, right? In Java, it's a little easier. Where'd it go? There. You replace all of that with the following, right? So you call the arrays method copy of. So that will copy that array, right, into a new array that has that length there, right? So it makes the array for you of the appropriate length, right? That length right there, copies the elements into the new array, and you're done, right? So it's a little bit easier to do this in Java than it is in C. Although it's not a lot easier. It's pretty much the same thing, right? All righty. So I guess I'll call it quits there for today. And then I guess what is the next lecture? Let me quickly look. So what am I doing? Oh, okay. So we're going to look at the linked implementation in the next class. The linked implementation looks different in Java than it does in C. But the ideas are all similar. So we'll take a look at what that looks like, and then we'll move on. All right. That's it for today. I'll see you next week.